Hello. In this lesson, we like to prove the fundamental theorem of calculus part 1, which is that, let's look at the statement, right? If f is continuous on a closed interval AB, then we constructed g of x, which is from a to x, integrating f of t, which is a continuous function. Okay, x is between a and b. And the conclusion is that g is continuous and differentiable on the open interval, and the derivative of g is f of x, i.e., g is an antiderivative of f. Okay, so to prove this, we're actually going to use the definition of derivative. So we're going to prove that it is differentiable for any point inside AB, right? And if a function is differentiable at a point, it is then continuous. Okay, so we use that result that we learned in chapter, I think it's chapter 2. But anyway, differentiable, then it is continuous, right? So we started out by choosing any point. Okay, so if x, we're going to let x and x plus h, right? Because we're going to quote the definition of a derivative. We choose x, and x plus h are both inside the interval AB. Okay, so we want to prove that, and the goal is to prove that the g is differentiable inside the interval AB, as we choose x arbitrarily inside the interval AB. Okay, to prove that, looking ahead, right, we want to construct g of x plus h, subtracting g of x divided by h, and then we're going to use this form. So before we do that, we're going to work on g of x plus h minus g of x. Okay, according to the definition of g of x plus h, here we have a g of x, right? We have a g of x. So subtracting g of x, right? So that's a g of x. And here is going to be g of x plus h, right? So if g of x is defined as such, and g of x plus h, so here is going to be x plus h. All right, so g of x plus h will replace g of x plus h. So we got this form, okay? G of x plus h minus g of x, okay? And then by a property of integration, just definite integration, okay, definite integral. So we're going to look from a to x plus h. We're going to split interval. Okay, we split that interval from a to x plus the interval of x plus h. Okay, so we split this integral into a to x, and then x to x plus h. And of course, for the same function. Okay, so for the same function. Wait a second. Okay, so right here, over here. Okay, so you can see this interval from a to x plus h is split into a to x and x to x plus h, subtracting this other one. And this way, these two will make 0. So in the end, g of x plus h minus g of x would be equal to just this part. All right, so we got the numerator. And assuming, of course, when we're going to assume h approaching 0, okay? And what is more, we're going to assume h cannot be 0. H cannot be 0, okay? We just, this can be easily done because when we consider limit, right? When we consider limit, we h approaching 0, but h doesn't have to be 0, okay? Especially we're going to divide by h. So on this part, we will have 1 over h, okay? 1 over h multiply. Okay, so I'm going to write another form. It's a different way of writing it. So 1 over h, we're going to keep it outside. And g of h, and this piece, we're going to replace it by that. Boom. Okay. And now we're going to process. We're going to apply, because we know that f is continuous. Okay, f is a continuous function. Assuming, okay, for convenience, this is just for convenience. For h is positive, okay, we know that f is continuous. If f is continuous on AB, right, and x is chosen inside of AB, therefore f is continuous. F is continuous on this interval. And this interval would be x to x plus h. Okay, since we assume h is positive, so x plus h is larger than x. So this is a meaningful interval. All right. By extreme value theorem, okay, since f is continuous on this interval, by extreme value theorem, right, we know there's a max and min, absolute max, absolute min, okay? We know, right, they are absolute max and absolute min, right? So there's a u comma v, and these two numbers are going to be inside this interval, such that one is local max and one is absolute max, such that one is absolute max and the other one is absolute min. Okay, so f at u is absolute absolute minimum. F of v is absolute maximum. Absolute max, absolute min on this interval. Okay. Let me mark it. Okay, let me write it down in parentheses. Absolute minimum and absolute maximum on the interval of on this piece, on this closed interval. Here we go. All right, with that, we know that because H is positive, right? So this piece, right, we're gonna look at this piece. We'll come back to look at this piece. On this piece, F has absolute minimum. So this should be greater than or equals to, right? If this function, if this is replaced by its absolute minimum, and on the other side, of course, it will be replaced by absolute maximum. Okay? And integrating this, right? We know how to integrate this part because lowercase m is a constant. So that's going to be just m multiply h. Okay? And that piece is just going to be capital M multiply h. Therefore, this piece in the middle is squeezed, right? I'm going to bring this back here, right? So this piece equals to lowercase m times h, uppercase m times h. So it's squeezed in between. It's squeezed in between. Since we've been assuming h is positive, okay? For h is negative, we can do similar things, except the inequality will have to switch directions, okay? But that can be handled in similar manner. But anyway, so for the moment, we choose h is positive. And now when we divide each side by positive h, right? So we divide each side by h. So divide by h. So this will be divided by h. Let's multiply 1 over h. So this integration, which is that piece over there, is between the absolute minimum and absolute maximum. In other words, right, we also have this piece, right? So we're going to substitute the lowercase m by f of u. U is between u and v in this interval, okay? F of v will substitute the capital M, okay? And also remember, u, v are inside that interval. Okay, these information will all get to be used. So now we get this piece of information, right? i.e., that is, we know that this piece is the same as that, right? That's the same as this. So this piece is substituted by that. So over here, that will be true. All right. And now it's time to take limit. Of course, we're going to let h approaching 0. Now, as h approaching 0, what will happen? If h approaching 0, because uv is inside this, right? As h approaching 0, u would be approaching x, v would be approaching x as well, right? Because uv are between these two numbers, h approaching 0. Therefore, we're taking limit. As we're taking limit, so we're going to take limit, okay? Limit as h approaching 0, f of u, right? F of u It's a continuous function, right? So it's approaching f of x. And as h approaching 0, f of v is also going to be approaching f of x. So the function, right, is squeezed. This form is squeezed in between. So by squeeze theorem, okay, by squeeze so by squeeze theorem, okay, by squeeze theorem, this limit as h approaching 0, this limit as h approaching 0 will be f of x, because the lower function and the lower one and the upper one, they both have the same limit, which is f of x. So by this time, we have proved that g is differentiable at every point inside, okay? So that is, we just want to illustrate, right? G is continuous. I'm sorry, it's differentiable, right? Because we use the definition of differentiable. A derivative is differentiable at every point, at any x, inside AB, right? Thus, f is differentiable inside AB. So now, right, if f is differentiable inside AB, then f is continuous in AB. Okay, f is then continuous in AB. Then, but the theorem wants us to prove that it is also continuous on the endpoints, right? So we're going to use right end limit, left end. So at A, so we're going to prove. So for prove this differentiability, we're going to apply the left limit and right limit. Okay, hold on. I need to wear my glasses. So for A and B equation, right? For A, right, for point A, we're going to, all the proof can be done. We're going to choose A, so A plus, and H is positive. So this will be right continuous. So this will be right continuous. Okay, right differentiable and right continuous. Okay, so right continuous. Okay, so that would demonstrate it is right continuous. And for B, right? For B, it's going to be left. For B, it's going to be B, but we're going to let H approaching from 0, from smaller than 0. This is from larger, okay? And so this is B, and H is negative, right? So this is left continuous. Okay, so left continuous. Left continuous. All right. So that has been proved that G is continuous on the closed interval. Therefore, G is continuous on the closed interval. Then you say, well, if it is right, do we have right differentiability, left differentiability? No, we don't. Okay, we can only use this to demonstrate that it's right continuous. Okay, it's right continuous, left continuous. So that's the proof. As far as for H is negative, right? Then you say, well, we have only assumed H is negative. What if for H is positive? What if H is negative? If H is negative, okay, if H is negative, we will have the interval is going to be just changed very slightly. It's going to be changed just slightly. Okay, so I'm going to copy and paste this part and show you, right? For H is continuous, how would that be done? Okay, so I'm going to show. Okay, for H is negative, right? From this part. It's not, the textbook didn't do this part, but I'm going to show you how this part will work, right? Because sometimes you just wonder, really, right? So for H is negative, okay, for H is negative, what will happen? There will be a couple of changes because when H is negative, X plus H is smaller than X. So we're going to switch these two. So it's going to be X plus H and this is X. But remember, H itself is negative, right? So this interval would be X plus H to X. If we arrange it from larger to smaller, the extreme value theorem still applies. So we still have the absolute minimum, absolute maximum. So we would have this relationship, right? We still have this relationship. We will still have this same thing. However, once we get to be here, we divide both sides by H. This will be switching directions. This will be switching directions. Okay? This will be switching directions after we divide by H. H itself is negative. But no fear. So this will be switching directions. Okay, this will be switching directions, and of course that interval will have a minor change, which is a switch, right? It's really not fundamental. It's just a way to express from smaller number to larger number, and this will switch directions. Okay, this will switch directions, and this will still be true, even though H is negative, H approaching 0. And we can still apply squeeze theorem. We can still apply squeeze theorem, okay? Because this piece is squeezed between two, all right? Between two values, all right? I think what we did is okay. Yeah, it's just H is negative. H is negative. Okay, and so this result is still true. Okay, so that's the end of the proof. Okay, thank you for watching. So before we close, so let's go back to see fundamental theorem of calculus part 1. Okay, is that f is a continuous function as the function is being integrated. and we generate another function g. The g is defined on f. And g turned out to be the antiderivative of f. Okay, thank you for watching.